So just to give a bit of context, so this project is part of a team which is part of a bigger team called AI for Science, or Science Team in DeepMind. And the whole point of the science team is to leverage AI to pursue breakthroughs in impactful scientific problems, scientific challenges. So the whole point of this is that now, with AI, we have new tools, extremely powerful tools, that allow us to tackle or to face long-standing problems in science and maths from a completely different point of view. And in some cases, this new viewpoint, this new angle, allows us to make a lot of progress, to maybe even solve open problems, or if not solve, at least to gain a lot in our understanding towards solving those problems. So AI allows us really to have new opportunities in order to tackle those problems. And that's the main purpose of the science team. And one such long-standing problem is protein folding, and AlphaFold is like our flagship project that has done, well, a lot within this problem. Now, within the science team, there is the computer science team, or AI for algorithms discovery. And within this context, then the point of this team is to leverage AI to discover new and verifiably correct algorithms that are able to outperform the state of the art in impactful problems. And within this team, we have worked on two projects. The first one was AlphaTensor, and the one I'm going to talk about today is FunSearch. Both of them have been published in Nature. But let me start talking a bit about AlphaTensor, just briefly. So that's our first project. That's the way we started this team. And the whole point here is to use deep reinforcement learning in order to search for new and better algorithms to perform matrix multiplication. And when I say better here, I mean better in terms of the number of basic operations, scalar multiplications required to do matrix multiplication of different sizes. The thing here is that we were exploiting one property of this problem, which is that a matrix multiplication operation of a given size, of given sizes of the matrices, is essentially equivalent to a tensor, which is a 3D matrix, and then the compositions of this tensor correspond to algorithms for this matrix multiplication operation. So essentially, we were exploiting that property in order to, to use deep reinforcement learning in order to find the compositions of these tensors. Now, this works really well. The system that we end up building after quite some time, at the end, it ended up working really, really well. It's really great at finding, and in fact, it found algorithms that improved over the state of the art for many different sizes. And this is one of the ones that it found. It's really great, but one issue with this is that if you want to tackle a different kind of operation or a different kind of task that you are interested in, you have to change a lot of things, or you cannot even do that because we can only tackle those operations in which can be expressed as tensors. And this is a quite limited set of operations. So back then we were really fantasizing, like, wouldn't it be amazing if we could have a system like this that could be applicable to more general, to anything really, right? To more general tasks, computational tasks. And then by the time we were finishing this project, it was becoming quite clear that LLMs, well, they were kind of powerful. They were showing their heads, and you could see that there was a lot of potential there. So then we started tinkering, and we saw that, yeah, indeed, there was, yeah, it could be really interesting because to use them, because we could get code out of them, and we can search in the space of code directly. And that was essentially the beginning, the seed of FunSearch. Now, we could use LLMs to try to answer questions. Now, just to remind you, the questions we are interested in here are, as I mentioned before, open questions, like big challenges, problems that we don't know the solution. They are just essentially, they are not solved, right? So, or we don't know what the best solution is. So if we ask these kind of problems to an LLM, just naively create a prompt and then say, okay, give me a new solution and, for this open problem. Usually what we will get is, well, some kind of hallucination perhaps, or maybe some version of some piece of code that the LLM has seen at training time that is somehow related to the problem you are asking. But it won't be able to provide a novel, an innovative kind of solution, of solution in general. It won't, or I mean, it's extremely unlikely that it will do that, right? So that's the bad thing. But the good thing, the good part of this is that here we are dealing with code. And unlike natural language, the good thing about code is that we can run it. We can run it automatically. We can evaluate it automatically as well. And that's really powerful. Because that allows us to couple LLMs with evaluators. So essentially, we can use LLMs to produce all sort of programs, all sort of hypotheses, and then the evaluator will be the one in charge of filtering out the ones that are completely useless, but it will score the ones that are useful, and then we can also distinguish which ones are better than the others, and then we can use the best ones to feed them back into the LLM, into a prompt that will be part of the input of the LLM. So in a way, you can see this as making the LLM to be the creativity engine, so to speak, which it will produce all sort of outputs that might make some sense. Many of them will be completely useless, but that's fine. But some of them will be useful. And then the evaluator is the one providing the rounding, right? Which is as key here. And in fact, this kind of framework or this kind of solution is being employed nowadays in many projects and many papers because it's very powerful, right? And the good news also is that there are many problems out there that are hard to get solutions for, but they do admit an evaluator, an efficient and fast evaluator. Just think of MP problems, for example. So the good thing is that then we can use FunSearch and systems like this to we provide to those systems as an input the evaluate function, the evaluation function, and then we let FunSearch to deal with the hard stuff, with the hard stuff of coming up with solutions that perform well according to this evaluate function. Right. So before I go into how FunSearch works under the hood, I'm going to start by talking a bit about some results, some of the experiments we've been doing. So the first set of results is has a theoretical kind of nature. They are combinatoric problems in combinatorics. So I'm going to focus on an instance of the largest independent set problem, which is known to be an NP-hard problem. And the focus here is on a family of graphs that are known as the cap set graphs. And this cap set problem is important. Like within the math community, it has a high significance. So like for example, Terry Dow said that it is one of his favorite problems. So just to give a bit of an intuition about what this problem is about. So first of all, let me tell you that there is one instance of this problem for each dimension, for each number of dimensions. And the point of this problem is to find the largest possible set of vectors, of points, in the F3 to the number of dimensions, such that no three of those elements lie on the same line. So given that we have one such problem for every number of dimensions, we can look here what happens when n is 2. So we have 2 dimensions. And in that case, all the universe of possible elements is 3 squared, is 9, the ones you see there. And then we can start by building our cap set by starting with an empty set, with an empty cap set. And then we keep adding one element. So we start adding this element, then this element as well, then a third element. But here we have a problem, because as I mentioned before, we don't want to have, we have the constraint that we are not allowed to have 3 elements, 3 nodes, or 3 vectors in the same line. So we remove that one, and then we keep on going. So we have just another one and another one. So we have now 4 elements, 4 vectors. And it turns out that no matter how you do this, you cannot do better than 4, right? In particular now, if you try to add 1 more element, yeah, you cannot. And this is the case for n equal 2, but this is kind of an easy case, but as you move on, as you move to higher dimensions, as you can imagine, the problem becomes, well, extremely complicated, extremely convoluted. It's really difficult to make progress there. But the good thing is that this problem does admit a reasonable efficient evaluation function. So why is that? Well, first, it is easy to verify whether a set is a capset or not. So essentially, as I mentioned before, you need to check whether there are no more than 2 points in the same line. And that is something that you can do in quadratic time with respect to the number of elements in the set. And the second point is that you can measure how good a set is, right? And in this case, is how good a capset is. In this case, it's just about counting the number of elements. So it's super simple. The bigger the capset, the better. That's all we care about. So, yep, sure. Right, so okay, so the question is whether we're gonna arrange more points in this case. Just to mention, in this field, these lines, these curved lines are also count as lines. These ones here. So, yeah, that's why. Yeah, but it's a good question because, yeah, as we have mentioned that. So yeah, these are also lines that you couldn't put, like for example, this, and that. This is not valid, right? Yeah, thank you. Cool. So yeah, so we implemented this evaluation function, and then we started applying FunSearch to many different dimensions. Yep.
Okay, so you can check whether one solution is better than the other, but how do you prove that it's optimal solution for the problem?
Great question. We cannot. No, it's a great question. Yeah. So all we're after here is actually, yeah, and we'll go a bit through it a bit later. But yeah, we're not proving that this is the optimal. This approach doesn't allow you to do that. But it will provide you with new and potentially better examples, better constructions of the ones that are known, and maybe you can yourself, maybe you can try to do something about that in terms of trying to prove something. But yeah, but just by itself, you cannot. Yeah. So we applied FunSearch using this evaluation function based on these principles on many different dimensions. So yeah, and then we saw that FunSearch was easily able to find the state of the art on n equal 1, 2, 3, 4, 5, 6, and 7. And then for n equal 8, it was able to go beyond the state of the art, and it was able to find a capset of 512 elements, which is better than the previous state of the art of 496. And that was actually pretty impressive. Also taking into account that the search space there in n equal 8 is already is huge, like 3,900 elements. So yeah, that was really amazing to see. And in addition, we also tackled the asymptotic problem as n tends to infinity, as the number of dimensions tend to infinity. Yep.
Okay, so my question is, did you start with known 496 and after that improve this, or you started at the beginning?
Great question, yes. Yeah, the answer is we started from the beginning. We started from a very simple function that does essentially a very dumb baseline. But it's a great question. So because, as we'll see later, FunSearch allows you to start from whatever point you want, as you mentioned. And in some cases, it might be a good idea to start from there. In other cases, it might be, actually maybe the opposite, because it might be the case that good solutions are kind of a local optima within where they are, in a way. And also, another point is, in the specific case of the gap set problem, you have this set, 496. So when you look at the literature, these sets appear as a list of vectors. You don't have the actual function that constructed them. In some cases, for some of the results, you do, because you can see you read the paper, and then, okay, this set was built in such and such way. But in other cases, those sets were found just by some, I don't know, some kind of convoluted search in which eventually led to this set. But you don't have the code that directly produced that set. So there is a mixture of things there. But yeah, in this case, we started from scratch. Yeah, cool. So we applied this to the asymptotic problem of a sentence to infinity by using a different construction that mathematicians, they know a lot about. It's called admissible sets, and allows us to provide or to search for lower bounds for this case. And by using FunSearch, we were able to improve the lower bound as well. And that's great because, yeah, these two results are the first, as far as we are aware, in which we were able to improve the state of the art by leveraging LLMs in a way in which LLMs were key to finding this. We also improved the state of the art on other problems in combinatorics, particularly the Shannon capacity of cycle graphs and concurrence problems. But yeah, I won't go through them here. But if you want to know more about them, we talk about them in the appendix in the paper. Yep.
When you check this, when n goes to infinity, you first acknowledge the construction for n equal 8, and then manually proved some sort of bound, or what was the LLM that found the bound going towards infinity?
Right. So it's a different kind of way. So what we do is mathematicians have developed a different kind of construction. It's called admissible sets. It's a different kind of combinatorial problem in which, if you are able to find some constructions there, this translates directly into a lower bound for the asymptotic in the cap set, but it's not leveraging directly the case for n equal 8 or anything. It's a completely different kind of problem that essentially allows you to, so you build constructions in this new problem, and then this translates into a lower bound here.
Yes, but those constructions, with n growing, they were found by LLM automatically, yeah, or was a person engaged?
No. And again, I'm gonna briefly talk about that now, but is LLM found it by itself? I mean, FunSearch, essentially, LLM within this system found a function that led to this construction that itself led to this lower bound.
Okay, thank you.
But I will touch a bit upon that soon. So, yeah.
Yes. So I have a general question regarding those LLM searches. Do you have any idea on how to improve them, or how to guide them so that they can explore smaller space than the full space? Do you have any control over that?
Right. Yeah, I'll briefly go through it in the second part of the talk, but just briefly now, I mean, there are a lot of ideas there you can explore, really. From simply, I mean, the simplest way is okay, you have some controls, like, for example, the temperature in which you sample from the LLM. That's a simple thing, but also there is this idea of what do you ask the LLM to implement? Is it the whole program, or is it just a small part of the program? Because maybe you know that your solution is going to have this structure, and then you code it yourself, and then you let the LLM to implement the key part that you don't know how to implement, right? So if you limit a bit the search space in some way by leveraging domain knowledge about the problem, of course, that would be helpful as well. But yeah, there are many other ways, and I think this is a very really open problem. There are a lot of things there are a lot of ideas that you could really try. But I briefly also talk about this later.
Great, thank you very much.
Thank you. Cool. Okay, another one.
What is the feedback loop like? Do you put results back into the conversation, or do you have some reinforcement learning implemented?
Right, there is no reinforcement learning. I will talk about how things are in the second part, but just briefly, the main the main feedback is the score, or essentially the score that you get from the evaluator is taken into account. Is the main thing that you take into account in order to sample functions that you have already discovered, in order to create new prompts, in order to feed them back to the LLM. But I will go through it. Yeah. Good. Great. Okay. Keep them coming. So yeah, as I was saying before, yeah, what if you apply standard search on the solution space? So essentially looking for sequences of vectors, for in this case for the captured problem, what you could end up at the end is just this, right? So it's a list of vectors. And this is what you are looking for at the end. But if you get a piece of code that is able to construct the solution, you get a whole lot of information more that you can actually leverage. Like here you have a piece of code that you can try to understand. You can try to, to tinker with it as well. You can try to modify it and see what happens in the output. You can do all sort of things. And maybe you are able to gain some understanding about the problem that you didn't know before. And that's also another important point of this approach. It's not only about finding the state of the art or improving the state of the art, but also this is important. In fact, we were working with, in this project, we were working with Jordan Ellenberg. He's a professor in math. He's really top professor in math. And in fact, he was the author or the co-author, one of the co-authors of the main the main result in the captured problem. And when he was working with us, at some point he said, the programs supplied by the LLM is far conceptually richer than a mere list of vectors. I'm learning something. And then he mentioned something that he learned. So yeah, he was, in fact, he that knows a lot about this problem was apparently learning something by looking at the code. Now, as I said, he's an amazing professor, amazing researcher in math, but he's also a very nice guy. So maybe you could think that maybe he was saying this just to make us feel happy and encourage and keep working on this. But I'm going to give you an example about why this is indeed the case, why this is true. So this is a piece of code, the one in the left. This is a piece of code that FunSearch produced for the admissible set problem, which is the captured problem in the asymptotic case. And this piece of code was already improving the state of the art by a bit, but it was able to improve the state of the art already, starting from scratch. Now, we then look at the code, and then we realized that there were some irregularities there. In particular, we saw that this function treats triplets of coordinates in the same way. So then we started thinking that maybe, perhaps, there is some kind of symmetry about this problem that we didn't know about, and that the function is kind of exploiting. Now, this symmetry might be true or might not be, might be there or might not be there. We don't know. We haven't proved anything. But one thing we could do is to say, okay, let's assume that this symmetry is indeed there, and then let's reframe the problem in such a way that we make solutions or make the output of the functions to be, in fact, respecting this property, this symmetry. So that's what we did. We then reframed the whole problem, and in this sense, we restricted the search space by forcing solutions to be symmetric, and then we put them back into FunSearch, and then we run it again. And then what we got was a function that produces an admissible set that is much significantly better than the one that we were getting from here. And this is in fact the result that we are that I was showing in the table before. So that I think is a great way to see how systems like FunSearch and us can interact with each other and can complement with each other. And the interface here at the end is code. Code is something that both parts of this story can understand, right? And I think that's an interesting case in which this is clearly showcased. Now, one thing that we did before starting FunSearch was to tackle the capset problem using search in the solution space, and we were not. We failed completely. I mean, we were very far from the state of the art. So it's kind of interesting that by using by searching the functions in the function space, we were able to get very good results without a lot of effort. So why is it that searching the function space sometimes, often, tend to work so well? Do you have actually any answers to that? Because I don't have a proper answer. I have some hypotheses, but I don't really know. Do you have any ideas? And there is no wrong answer here. Because the function is a generalization.
Because by the function you are making some kind of rule where you can apply different sets of data to get an output. So you have that different rules. Of course, this is like high-level abstraction, but you are moving like going into the higher level of abstraction, and then you are moving around the different abstractions. I don't know if this is true.
No. But that's a good. I think that's a good guess. Like in a way, you move to a high level of abstraction in such a way that, yeah, maybe there is something there. Yeah. Is there any other other guesses over there?
Like I would say maybe it clusters the answers together somehow, and they are more dense in the original space.
Clusters answers.
Like the possible like good candidates for answers. So they come together, and like searching them, like finding them is easier because they come denser than in the original space, where you have like a lot of random points, and then by searching you will find like small number of good solutions. And here like they are together, and so if you hit the cluster, then you are near the good solution, and all of them are good somehow.
Right. So, and that's not how it's important, but I agree. So maybe in the function space, you have this.
It's smaller. The function space is smaller.
Yeah.
Right.
Yeah. In theory, it's huge, but yeah, in practice, I agree that implicit is kind of small. Yeah. So there is one more here. Yeah.
This is quite similar. So maybe if the answer is not completely random, then we can count off that function will compress well a pattern. And if we hit right function, we have right pattern extending the some bounds that maybe we checked, right?
Great. I really like that one. But yeah, I mean, by the way, all of them were really great, and they I mean, again, I don't know the right answer. Starting with that. But what I think and what we think in the team, that is what we think, and again, is a hand-wavy kind of explanation that is far from an actual answer to this question. But yeah, we think that many problems we care about are structured in some way or another, and maybe as a consequence, it is often the case that good solutions are also structured, and in this case, we mentioned this small commode of complexity. They have a small commode of complexity. So commode of complexity of something is the length of the sorted program that produces this something. So for example, a sequence, right? So the commode of complexity of AB is much smaller than the commode of complexity of a seemingly random sequence, right? And probably the problems we care about have solutions that are closer to the small complexity, the small number of complexity. So we believe that maybe FunSearch have this implicit prior that encourages solutions that have this concise functional description. Right. So yeah, let me move on in the interest of time, but to the second set of experiments. So this is a different, kind of completely different use case in which it has a more of a practical kind of flavor. It's about bin packing. So you probably know about what this is about. So it's yeah, you have many items of different sizes, and then you want to find the best way or a good way to putting them into bins. And yeah, the whole point is to make it so that in the most efficient way, right? Using as the least bins as possible. And here we focus on the online version of this problem, right? So in the online version, you keep getting items, and then each time you get an item of a given size, then you have to decide in which bin you put it into. Now, this might look like a toyish kind of problem, but it turns out that it's kind of everywhere. I mean, it's many real use cases. So it's at the core of problems like loading containers with items, or job scheduling, in which you have to put computational jobs to assign them into servers, right? And the whole point is to minimize the number of servers or containers or whatever you are putting items into. So we apply FunSearch there, and we also got pretty good results. So here is just an example. So we compare best fit, which is one very well-established baseline approach for online bin packing. We compare that with a function produced by FunSearch, and in this specific case, we saw that the number of the same set of items. So best fit required 52 bins, and FunSearch only required 50. This is, of course, a specific example. We can look at the function that FunSearch produced to do this assignment. This is the function you see. It's called a heuristic, and it has some comments. LLMs, as you know, produce all sorts of comments, and some of them are useful. Many of them are not in our case. But these comments are not produced by the LLM. These are, we wrote those comments just for ourselves to make it clear. And then, yeah, this function, I'm going to briefly go through it. So it has two inputs, two arguments. The first one is item. It's a float. It tells you the size of the incoming item. And you have bins. And bins is an array which of numbers. Each of them is the remaining capacity of the bins in which you can put the item into. And then the output of this function is an array of the same size. Essentially, you have a score for each of those bins, and what we do is we run this function. We get this array of scores, and then we pick the highest score, and then we put the item into the bin with the highest score. And that's something that happens after the function is run. Cool. So just briefly, so yeah, what it does is it initializes a score array with the same size as bins, and that will be the thing that the function will return. Then it penalizes bins with large capacities, and this is in the same line, in the same way as best fit does. And then from that, it diverges. So it extracts the index of the bin with the best fit. Then it gives a bonus to that bin. But finally, it penalizes it if the fit is not tight. And yeah, you can see that in the solution, it is true that there are many bins that are tightly fitted. But in any case, this is, of course, kind of anecdote. Okay, yeah.
I just wanted to ask, like, how does it compare to, like, the optimal solution? Because as I understand, you make, like, a choice at each time, and it might not be, like, globally optimal solution, right?
Absolutely. Right, so let me finish this slide, and I'm going to answer to this, but let me finish. So yeah, thank you. It's a very important question, actually. So just to briefly finish with this, of course we did we applied this to a benchmark, to a couple of benchmarks that are kind of well established, and in all cases, FunSearch or the functions produced by FunSearch were able to to outperform by far well established heuristics. Now, about your question, does that mean that this function here or the functions produced by FunSearch are better than any other approach in any possible use case? Now, the answer to that is no, completely no, resoundingly no. So the point here is that FunSearch is able to leverage, to exploit the particularities of your use case, in this case, the particularities of the distribution of items, the incoming items, in such a way that it produces a function that is particularly tailored towards that. So if for whatever reason your distribution changes, well, then you have to apply FunSearch again and come up with a new function that is applicable to the new distribution. But that's precisely the point. So it's as I mentioned here, this showcases how FunSearch can be used to automatically produce programs automatically that are adapted, that are tailored to your specific use case. So is that kind of answer your question? Or yeah. Like the thing is, in the online packing, it's difficult to have this notion of optimality. I mean, you can compare it to what would happen if you have information to about all the items, but that's never.
Because what I'm thinking, my question, maybe I asked it wrong, but in the end, when you have all the blocks, maybe there is like rearrangement of these blocks that is more optimal than the one that was chosen in this after these n steps of
Yeah, absolutely.
Okay.
But the thing is in an online setting you don't have access to the future. So in this context, it's not clear to talk about what the optimal solution would be. In fact, in this table, this percentage is actually with respect to the optimal solution if you had information to everything. So yeah. Anyway, so yeah, let me move on a bit. But yeah, just to finish with this part. Yeah. So I think that this point I think is really important about automatically adapting to a use case. Whenever I'm coming from machine learning and AI, whenever I or we hear about automatically adapting something, the first thing that comes to mind is neural networks, right? Neural networks, maybe the neural networks and deep reinforcement learning. But the good thing here is that we have code as an output, and I think that gives us many advantages over neural networks. So one of them is that it's very easy to deploy, right? You don't need TPUs or GPUs. You can just run the code on a CPU usually, and it is really fast usually. Second is that it is not a black box. So essentially, neural networks are essentially black boxes, but here you can look at what's inside, and you can try to understand what's there, right? So it's easier to debug. It is understandable. It is also more predictable, and also more scalable. Great, so that's the first part of the presentation. Now I'm going to talk a bit about what's under the hood, how FunSearch works. So, by the way, I usually stop here and ask if you have more questions. Okay. Okay.
Thank you. I'm a bit slow. It's still regarding the first part of your talk. You mentioned that FunSearch found an algorithm which apparently exploited a symmetry, right, with these tuples, but it was not quite clear. I was wondering, you know the solution is correct because you just check it, right? It's a cap set. Yeah. Did you consider asking the LLM to also produce a formal proof of correctness? Because I guess then maybe it would explain that there's a symmetry and use it, something like that?
Yeah. I mean, actually, it's a great question. So I'm gonna. One thing I will mention later is that well, the kind of LLMs we've been using here are not too big. Of course, we could say, okay, we can put this solution and ask this to a big LLM, and I know we haven't done that actually. I mean, we should, but I could be extremely surprised if we get something meaningful out of that. Maybe. I mean, yeah. Nowadays things are I mean, it's been a year since we work on that. Nowadays, yeah, we have things like O1 and many others. I don't know. Who knows? Maybe they're able to give some kind of hint. But about the actual LLMs that we use here, they are middle-sized, and the reason is that here we want a trade-off between LLMs that are powerful enough to provide good, interesting solution or interesting hypotheses, but also we want them to be very fast because the faster they are, the more we can explore the space. And in this trade-off, LLMs like our middle-sized kind of LLMs are pretty good. And those LLMs, I don't think they really understand the problem. It's more like they are good at producing good solutions. That I mean, good, like in, you know, they have been trained on a lot of code. So yeah, they're able to produce some interesting bits of solutions every now and then, and that's the main point. But adding comments about the problem, we have tried that. Adding comments in the prompt usually doesn't help, for example.
So maybe they just saw that often symmetry helps, so let's try it here, and it just worked. Is that maybe how it?
I could imagine that somehow there was it produced some program that had these indices of in the elements, and it was leading to better results. So this program went back to the prompt, and maybe it keeps exploiting this thing, and somehow it kept getting better results. I think that's kind of what was going on, but I don't really know.
Thank you.
Right. So yeah, let me keep going. So I guess I have like 20 minutes left or so, or 15. Okay, good. So yeah, as I was saying, LLMs by themselves, they cannot solve, or they cannot provide interesting solutions to the problems we care about, and I'm talking about open problems, right? So they, as I mentioned, they often come up with plausible background outputs, but the good thing, as I mentioned, is that we can couple it with some runtime. And here we are using Python, so Python runtime, to provide the grounding. And then by putting these two things together, what we can do is searching in the space of code, in the space of functions. And what we do is we do that by essentially using evolutionary kind of search. Just to get a bit of an intuition, what we do here is, well, first of all, we have this score map of functions. So here, every point here represents a function in Python, so that regions in red are interesting functions, and regions in blue are, well, not interesting. So we usually start a problem by specifying a very, very simple function, like solve v0. And this simple function usually is in the low interesting region of the space. But what we can do is we can create a prompt by using this function, and then adding a new header, solve v1, and maybe some comments saying improve over solve v0, and then we use that as a prompt that we introduce into the LLM. And then the LLM, we can sample from this LLM a few times, or as many times as we want. But no matter how many times we sample from it, it is quite unlikely that we were able to go to the interesting region of the space, right? So we will get new functions that lay on the neighborhood of the original solve v0. But what we can do is, given that we have an evaluator, we can check which functions are better than the others, and then we can leverage those, and we can use them. We can put them back into the prompt of the LLM, and then we can sample again, and then we can repeat this over and over. And by doing so, we are able to then move towards the interesting part of the space. Okay, so to be a bit more specific, so we start any new problem by having a specification as an input, as a specification of the problem. The specification of the problem essentially has two parts. So one is the initial function we want to evolve. As I said, it's usually a very simple function. And then the second part is the evaluate function, right? So the function that will evaluate the outcomes, the outputs of the LLM. So we start with the initial function that we provide, the one up there, to start populating a programs database. So where we will put all the functions that have been found by the LLM, at least the ones that work or that run. And then at any point in time, what we do is we sample from the programs database 2 functions. Each function in the programs database will be sampled with a likelihood that is proportional to the score that it got. And then we create a prompt. So we create a prompt with these 2 functions, and then we will create a new header with a third. It will be the third function, and then we let the LLM to complete that. So we put that as an input to the LLM, and then we will sample a few times, and then we will evaluate each of those new examples. Some of them will not run, but some of them will, and then we will score them, and then we will put them back into the programs database. So conceptually, the framework is pretty simple, as you can see. There is no RL, really. It's just pure kind of evolutionary kind of way of improving. And then, yeah, you get this kind of self-improving loop that keeps getting better and better. And now, at any point in time, you can, of course, check what the best solutions have been found so far. Great. So just some more details about how it works. So as I mentioned before, we use pre-trained LLMs of a size that is not too big, because there is this trade-off that I mentioned before. So yeah, for this project, we have been using Cody for the PAN2 family of models within Google, but we have also used an open source model. It was StarCoder, and if I remember correctly, I think StarCoder had around 15 billion parameters. So that's the kind of size I'm talking about. And yeah, this is kind of a good trade-off. Another, the second point I would like to mention about LLMs is that we haven't trained nor fine-tuned any LLM. We are using LLMs straight away. We are not touching them at all. The second point here is that we have implemented this approach as a distributed system. So in practice, what we have is quite a big system of asynchronously connected nodes. So in a normal experiment, we will have 15 LLM samplers that send outputs to around in the order of hundreds of evaluators, and then all these nodes are connected to this central node that is the program database in which all functions that are interesting are kept there. Now, another important point is that of a skeleton that I briefly mentioned before. Oh, yeah, there's a question there.
Yeah, so I have a question about because this approach uses the genetic algorithm, right, to find the best function, and LLM is used to, let's say, put those 2 functions that were sampled together. And based on my experience with genetic algorithms, they tend to find a solution. They struggle with diversity in the population. Yep. So I wonder, how did you face this problem? And if so, how did you solve that?
Yeah, great question. Yeah, we found a bit of that problem. Yes. So there is this is with diversity, that if you don't keep diversity, or if you don't encourage diversity in the programs database, the whole process can relatively quickly converge to a local optimal. It's far from. So we did two. We added 2 mechanisms to encourage diversity. So one of them is to group functions into clusters in the way that functions that produce the same output when you give them the same input, they are all clustered in the same group, in the same cluster. And then when we sample, we actually sample clusters instead of functions. So you don't overrepresent functions that are equivalent, and that helps. And the second thing we do is that we add an island-based kind of approach on top, so that you in practice, what we do is we evolve 10 populations in parallel, essentially 10 programs databases in parallel, if you want to see it that way, in such a way that every 4 hours we exchange information between them. In practice, what we do is we take the worst half of those islands, we get rid of them, and then we start populating those islands, restart populating those islands with the best, with some of the best individuals from the other islands, and then we keep iterating this. That's also helped a lot. Yeah, thank you. Cool. So yeah, about this, the last point of the skeleton, it's kind of related to what I mentioned before, over that question over there. So by skeleton, I mean all the code that you know that it could be interesting, that is important or interesting to get to the solution to your problem. This, for example, boilerplate code, or maybe the structure of a well-known algorithm within the problem you are tackling. And then you let FunSearch to evolve the critical part of the algorithm that governs the behavior of that algorithm as a whole. Like, for example, if you want to traverse a big graph, maybe you can implement yourself the way you go from one node to another, but then you let FunSearch to evolve the function that chooses which node to go next, for example. The whole point here is that, again, what we are after here is to solve problems. To solve other problems, and the point is, there is no way you can cheat here, right? So the more information you provide, the more the chances you have to get something useful. Yep.
So did you try to explore like what's the practical limit of, I guess, size of the function that the FunSearch can produce?
We didn't explicitly aim for that or try to do that. One thing we did actually related also to the question about the clustering functions is when we sample a cluster, then we had to sample a function within this cluster, and then we encourage functions that we gave more likelihood to functions that were shorter. And the objective is, at the end of the day, you don't want if you prefer simpler functions to more complex functions if they are similar in terms of behavior, if they perform the same thing. So we believe that was useful. But yeah, in terms of the length of the functions, yeah, we've seen functions of like say 50 lines of code, maybe in some cases a bit more. But it usually for at least for this kind of problems, it is not a good measure of the actual quality of the function. So we didn't really explore that. Thank you.
Sorry, quick disclaimer. We have like 10 minutes for this talk, so just keep that in mind.
Yeah, I think we have. Could you
go back to this diagram? Okay.
Yes.
So this is an arbitrary. Okay, thanks. Arbitrary design of the system. Have you thought maybe of adding another component? Because for every combinatorial problem, which is hard or intractable, there must be a set of other problems which are already solved. So they have programs. There exist programs, database, kind of building blocks. So have you thought of adding
yes,
a building blocks database to make it the whole process more efficient?
Yeah, great question. Yeah, that's definitely something super interesting, like adding extra information, extra libraries, or extra pieces of code of a related problem. And you can do that in many ways. Like one way would be just to add part of that in the prompts, or maybe sampling in different ways each time. In another way would be to fine-tune the model by fine-tuning in all this kind of specific code that is related to your problem. All this is super interesting, and we are like, yeah, we didn't try that for the purpose of this. We were trying a bit of this at some point, and just to answer this briefly, is what we were trying with FunSearch, and it's something I mentioned at the very end, is we were trying to make choices. Whenever we have a choice to make, we chose the simplest possible option. And the simplest possible option usually turned out to work really well, actually. And that was really good. But yeah, those are things we were, of course, discussing, and I think they could make the system even better. Yeah.
After your talk, I would like to return to home, download your Git repository with the FunSearch, so re-implement the class of LLMs, and try to solve Olympic computer science examples from this year, for example. Is it enough just, to re-implement the LLM class, and how many LLM calls we should count with if you would like to solve the similar problems like this CAP-set, for example?
So, hold on. So is your question like how to apply FunSearch to, or whether there will be things to change when applying FunSearch to things like Olympic kind of competition problems? Or
no, I mean there are known, let's say, problems in computer science that are also similar to the problems that you shown. And you published a year ago the FunSearch in the GitHub. Which don't have implementation of the LLM class. So I suppose it is job for us to, if you would like to use this code, to re-implement this class. How many LLM calls you had during your research?
Right, yes. So for the hardest problems, particularly, the CAP-set problem, in order to find the best solution for n equal 8, that was the hardest problem we were faced, and that was around 2 million samples, and not even. I mean, that was that was the one that required more samples, and actually not even all experiments got that result. So in some experiments converge to a lower solution, but all experiments. I mean, just to briefly mention, to briefly answer, it's in the order of a few millions. Maybe is to briefly go through ablation experiments. So we designed ablation experiments. I nearly the end, so I think we will get there. First of all, we compared changing the LLM, so how important a specific LLM is to get results. Here we compare Cody, which is in blue, with StarCoder. Essentially, these two models, they are not massive differences, as you can see. They behave kind of the same. And then we compare with what we said there, random. So random here is our implementation of a genetic algorithm in which we specified many unary and binary operators and mutation over the code. So essentially, it's our own implementation of a genetic algorithm. And this was way worse than using LLMs. And the second one is, the second ablation experiment is taking FunSearch as it is and then removing one component. So just briefly speaking, so the most important, or the one below, the one in orange is without evolution. So the one in orange is you take the original function and then you keep sampling the LLM, from the LLM. And as you can see, it's really bad, right? So it converges quite quickly to a very poor solution. The next one, the one in pink, is just without using a skeleton. It's also, for this specific problem, it was also really bad. We have the yellowish line is without diversity. That was about if the idea I mentioned before about using islands. So if we don't use islands, results are worse, but by some margin. And then finally we have without merging, which is the green line. The green line is so as I mentioned before, we take two samples from the database in order to create a prompt, and we did that based on the intuition that you have two parents, and then maybe the LLM is able to combine ideas from these two parents. But in practice, it turns out that it's not that important, and if we just use one parent in each prompt, it works almost as well. Great. So for which problem is FunSearch useful? So first, the key part is that you need to have an efficient evaluator. That's key. And the second point that is desirable is that you have a smooth scoring feedback. So this is possible to to tell for a couple of functions, you can tell whether one is better than the other, so that you can choose the best ones, and then they can lead to even better ones down the line. And finally, if you have prior information about the problem, that's good, because you can leverage it in order to build a good skeleton. I believe this is just the beginning. In this work, as I mentioned before, we have striven for simplicity. So whenever there was a choice, we went to the simplest one. And that means that this is conceptually a very simple kind of approach. So it's a strong and simple base that we can build on in the future. And by we, I mean really everyone. And finally, the second point is that we've been using here LLMs as in a plug-and-play kind of way. So essentially, as LLMs get more powerful and also faster and cheaper, we believe that that can improve. They can only improve the efficiency and how powerful these kind of methods are. So yeah, finally, I would like to thank the FunSearch team, the CS team, that they are really, well, amazing people. It's great to work with them. And of course, thank you everyone here. All the questions have been great. Thanks a lot for that, and thanks a lot for your attention. And if there is time for more questions, I don't know, I'll be happy to answer. Thank you.